at the concept of atomic radius. So atomic radius. This is going to be fairly important when we start to look at things like molecules and electronegativity. We'll be able to see a lot of the factors of atomic radius when we look at intermolecular forces later on in this course. But for now, we just need to understand what are the trends. There are certain trends along the periodic table about atomic radius. And what are those trends? And well, to understand those, first we need to understand two principles. And the first one is this idea that there is a ton of room inside an atom. If I've got an atom with this being its nucleus, the difference between the radius of this nucleus, so let's say this, we'll call this little r, we'll call the radius of the entire atom, big R. Big R is about 50,000 times little r. There is most of this area right here is just empty space. So when we talk about how the atomic radius is going to change, it's not going to matter how much stuff there is. It doesn't really matter how many protons or neutrons or electrons are physically in this space because there is so much extra room. But the thing that is going to matter, the thing that's going to matter a lot is, you may have guessed it, good old Coulomb's law. Coulomb's law is going to be the main contributor to a changing radius. So we're going to be looking at what factors will affect that radius. And we're going to see that as Q goes up, then radius will go down. And we're going to see that as the force goes up, the radius will go down. Okay? All right, let's look at our first trend. The first trend is going to be across the top of the periodic table. So let's look at some examples. We're going to use lithium, boron, nitrogen, and fluorine. Now, let's first think about how many protons do each of these have. Lithium has 3 protons, boron has 5, nitrogen has 7, and fluorine has 9. So my number of protons is increasing across the right of the periodic table. And what this is going to do is it's going to cause my overall atomic radius to shrink. Remember, even though I'm adding stuff, there's plenty of room. There's plenty of room for all of these extra protons. I'm not going to take up too much room. I'm not going to have to, expand my radius because there's more stuff in there. However, each additional proton is going to cause my charge to go up. So Q1 might be 3 with lithium, but for boron, Q1 is 5. For nitrogen, it's 7. For fluorine, it's 9. Those numbers keep going up. So according to Coulomb's law, the higher my proton count, the greater the force that's going to be pulling in these little electrons. So as I go from left to right on the periodic table, I'm going to see a shrinking radius. So from left to right, my radius will decrease. That's a terrible A. There we go. So this should make sense because each of these electrons are in the same shell, right? If I let's look at this electron compared to this electron, compared to this one, compared to this one. All of those are going to be in the same shell. They're going to have the same number of electrons that are trying to keep them away from this nucleus, okay? So that's going to be our first trend. Across the top of the periodic table, we're going to have a decreasing radius. So let's put that on a table here. Here we've got a periodic table. And so across the top of this, our radius decreases. Okay? Well, what about going up and down? How's that going to be different? Well, here I've got lithium, sodium, potassium, and we can see that these are in my first column on the periodic table, and they are right on top of each other. What do you notice right off the bat about these? Well, if we look at these, I can see that lithium, it's going to have 3 protons, sodium's going to have 11, and potassium is going to have 19. And so my proton count is going up, and so because of that, this closest layer, right here, this closest layer, you might have noticed, these electrons steadily get closer. However, on top of those electrons, each time I go down a row in the periodic table, I am adding layers. So lithium only has 2 orbitals. It only has 3 electrons. It really can't hold that many. So it only has these 2 orbitals. But sodium has 1, 2, 3 orbitals. So let's write that down. So lithium has 2 orbitals, sodium has 3, and potassium has 1, 2, 3, 4 orbitals. And so we can see that the addition of these orbitals is going to increase our overall radius. Now, a big factor in that is going to be this idea that while the electrons here, while this electron is attracted to this atomic nucleus, it is also repelled by the electrons that are closer. So this electron right here is going to be repelled by these electrons, but it's going to be attracted to that nucleus. Now, these electrons aren't always right in front of it. Sometimes they're moving to the other side of the atom, so they're not always going to be pushing this away with as much force. And so they're not going to be pushing away as much as these protons are going to be pulling in. And we'll talk about that factor in our next video. But we should recognize that this electron right here, this electron is going to experience some repulsion from the other electrons in the atom. And so with that trend in mind, as I'm going up the periodic table, my radius will decrease. So we're tracking our decreasing radius. But as I go down, my radius increases because my orbitals increase. So let's put that on our periodic table over here. So as I go up periodic table, R goes down. So radius decreases. Well, what that means is as I'm going from the bottom left to the upper right, my overall radius will decrease. So what could we say is our largest atom? Well, that would be francium right here. This is going to be my lower left. Francium is going to be my largest atom. Now what's going to be my smallest atom? Well, that would, of course, be helium right there. But helium and the other noble gases, they are not reactive. So they're not going to do anything. Fluorine, however, is very reactive. So if we put a barrier right here, and we look at only the reactive elements, well, fluorine is going to be my atom with the lowest radius. And this causes fluorine to be extremely electronegative. That's a concept we'll look into later. And it causes fluorine to be extremely reactive. It's been called the devil's gas because anyone who's tried to make fluorine has most often died doing it. There are tons of horror stories in chemistry of fluorine killing people because it's so reactive that it just starts reacting with your lungs if you breathe it in. So this is our overall trend. As we go from the bottom left to the upper right, our atomic radius decreases.